So now that you have a better understanding of the various classes that provide key features in the fork join framework, we're now going to turn our attention to the inner workings of the fork join framework, which I actually find quite fascinating. And hopefully I can convey the way it works to you in a way that you'll also have a better understanding of. And once you have a better understanding of how it works, I think you'll see why this is such a powerful framework for doing parallel computation in modern Java. So we're going to talk first about how the fork join framework implements worker threads. So if you recall our discussion earlier, non-fork join clients, that is, parts of Java code that are not being run yet with the worker threads of the fork join framework, can insert new tasks into the fork join pool's shared queue. So for example, a client could come along and call submit or execute or invoke and put a fork join task into the queue. And this shared queue is used to feed the so-called work stealing queues, or DEQs more specifically, that are managed by the worker threads in the common fork join pool. And we'll talk momentarily about what these cool work stealing DEQs and queues do. But for right now, let's just focus on the threads. Each worker thread in a fork join pool runs a loop that scans continuously for tasks or subtasks to execute. And the goal of the whole thing, the whole purpose behind the fork join framework, is to keep these worker threads as busy as possible. So the idea here is, as long as there's work to be done, then we want these threads doing that work. The worker thread has a double-ended queue, which is what's known as a DEQ, that serves as its main source of tasks, or maybe a better way to put it, its initial source of tasks. And if you take a look at the DEQ implementation, which is, of course, nested inside of the underlying Java fork join pool class, you'll see that there's a nested class called work queue. And work queue has some key methods, namely push, pop, and poll. It's got other methods too, but those are the ones that are the most important, and we'll talk about them. So here's the way things work. If a task that's run by a worker thread, so now we're assuming we're inside of the fork join pool, or a fork join pool, could be the common fork join pool, could be a user-defined fork join pool, whatever it is, if a worker thread in the context of the pool calls fork, the newly created task or subtask is pushed onto the head of that worker thread's DEQ. So you can see here, when a fork is called, then that will call in turn push, and it'll push that object onto its DEQ, onto the head of the DEQ. By the way, you can read more about this in the paper at the bottom of the page, bottom of the slide, written again by Doug Lee. The worker thread processes its DEQ in last in, first out order, which is basically the stack discipline. So it's a LIFO order. And there's a very good reason for this. What it does is it pops the task or the subtask from the head of its DEQ, and then it runs that task to completion. So it calls its compute method basically until it's finished. And remember that join will pitch in to pop and execute subtasks. So that's what join does. It'll pop the subtasks and run them until things are done, which is that collaborative Jiffy Lube model of processing we talked about before. So why is it the case that the worker threads in the Java fork join pool use LIFO in order to be able to handle the work that they're given? And the reason it uses LIFO is to improve locality of reference and cache performance. And the assumption here is that if you have pushed a task or a subtask onto the DEQ, then the next time you get work to do, you want the one that's been there the shortest time. And that's something that's often referred to as the fresh work before stale pattern. And this is very common in all kinds of computing environments where you want to try to leverage locality of reference. And the reason you want to leverage locality of reference is because most likely those elements are still in the instruction and or data cache. And therefore, it'll take less time to process them because you don't have to go out and retrieve them from some kind of storage like a swap storage or something like that. So that's the end of the overview of worker threads in the Java fork join framework. And again, the key thing to remember about all this stuff is that each worker thread has a deck. And when the worker thread's given work to do, it pushes it onto the top of the deck. And then when the join call is invoked, then that worker thread will start popping things off of its deck and will run them to completion. And it does that whole process in last in, first out, or LIFO order in order to be able to enhance locality of reference, which thereby will be more likely to do a good job with data and instruction caching. So keep those things in mind. That type of question often shows up on quizzes, so it's a good thing to be familiar with that.